determining mechanism of reaction. So, so there are some method by which you can determine the mechanism of reaction. That is, by analyzing the product, you can determine the mechanism of reaction, and by using some isotopes, and by trapping the intermediate, and by doing the crossover experiment and stereochemical evidences, you can determine the mechanism of reaction by which ways your reaction is going. Okay, so the first point in that is product analysis. So by analyzing the product, so by what? Analyzing the product, you can determine the mechanism of reaction. You know, the mechanism is nothing but it is a step by step explanation of your reaction mechanism. It is nothing but the step by step explanation of reaction. Suppose in your reaction A is convert to B, A is convert to B. So mechanism explain how A is convert to B. Mechanism explain how A is convert to B. It explain in which way your reaction is going on. So by analyzing the product, you can determine the mechanism of reaction. So to understand this concept, let me teach you an example. That is a reaction of propene in presence of HCl. So structure of propene, CH3, CH3, CH2, CH2. So this is the structure of propene, reaction of propene with HCl, with HCl. You will get two different types of product. You will get two different types of product. When this HCl react with this propene, you will get two different types of product. And I will write the product name of that product, structure of that product. You will get one chloro and two chloropropane, CH2, plus three Cl. Okay, so when this propene react with HCl, okay, you will get two different types of product. That is one chloropropane. So this is your one chloropropane. This is your one chloropropane, two chloropropane. This is your minor product and this is your major product. Okay, so by analyzing the product, you can determine the mechanism of reaction. So addition of HCl to propene gives the formation of 2-chloropropane as a major product. Addition of HCl to propene gives the formation of 2-chloropropane as a major product. This clearly indicates that the formation of 2-chloropropane as a major product. This clearly indicates that the mechanism involves Markovnikov's rule. The addition reaction takes place on the basis of Markovnikov's rule, and in this reaction there is a formation of more stable secondary carbocation. There is a formation of more stable secondary carbocation. So you are getting two products when you do this reaction, addition of HCl to propane. You will get two different types of product. Okay, that is 2-chloropropane is a major product and 1-chloropropane as a minor product. So by analyzing the product, you can say that in this reaction there is a formation of carbocation intermediate. There is a formation of carbocation intermediate, and the addition of HCl to propene involves the Markovnikov's rule. So Markovnikov's rule is nothing but what? The negative part of your reagent adds to the carbon that having less number of hydrogen. Negative part of reagent, so the addition of this HCl to propene involves the Markovnikov's rule. Okay, so this your reagent H plus and Cl minus. So negative part in this reagent is Cl minus and positive part is your H plus. So Markovnikov's rule, the statement is said that the negative part of reagent adds to the carbon which having less number of hydrogen. Okay, so in this reaction, what when the carbocation form, okay, so the middle carbon having less number of hydrogen, so that negative part is adds to the carbon that having less number of hydrogen. Okay, so by analyzing the product you can determine the mechanism of reaction. So let's see its mechanism, so you can understand in detail, you'll get the detailed understanding of this. So in reaction mechanism, a step explanation of your reaction. Okay, so in the reaction mechanism, first step is what? This your propene react with HCl. Okay, so this propene having carbon double bond. Okay, so that carbon double bond, it's a this carbon double bond, it acts as a nucleophile in this reaction. It's a high electron density center. This carbon double bond, it's a high electron density center. So this pi bond of this propene attack on H plus. Okay, so it attack on H plus. So CH3 CH2 CH2. Okay, if this hydrogen add to this middle carbon, okay, if this hydrogen add to this middle carbon, you will get the formation of primary carbocation. You will get the formation of primary carbocation. Okay, you will get this type of carbocation. And if this hydrogen add to this terminal CH2, you will get the formation of secondary carbocation. Primary carbocation, and this is your secondary carbocation. Hyperconjugative carbocation having only 2 Cl minus attack on this carbocation. Okay, so Cl minus attack on this carbocation, same this Cl minus it attack on this primary carbocation, and you will get this primary as well as you will get this 1-chloro and 2-chloropropane. You will get this 1-chloro and 2-chloropropane. Now once you get this product, okay, we'll get the this 2 chloropropane is in a major amount. So by analyzing the product, okay, suppose this your 2 chloropropane you will get in 90%, and you will get only 10% of this 1 chloropropane. So by analyzing the product, okay, by analyzing the product you can determine the mechanism of reaction. By analyzing the product you can determine the mechanism of reaction, okay. So by this analysis you can say that this reaction, okay, the addition of HCl to propane, this reaction involves the formation of carbocation as an intermediate, okay. This reaction involves the formation of carbocation as an intermediate, and it follows Markovnikov's rule. Addition of HCl to propane follows the Markovnikov's rule and involves the more stable secondary carbocation. It involves more stable secondary carbocation. Involves more stable secondary carbocation. So this is the just example of product analysis. So by analyzing the product you can determine the mechanism of reaction. For that we have taken this example, that is this HCl, the addition of HCl to propane, at the addition of HCl to propane. So when you add this HCl to propane you will get the two different types of product, that is 1 chloropropane and 2 chloropropane. So these two are the position isomer. These two are the position isomer, 1 chloropropane and 2 chloropropane. But you are getting this 2 chloropropane as a major product, 2 chloropropane as a major product, and this 1 chloropropane as a minor product, because this reaction involves the formation of more stable secondary carbocation, and the addition of HCl takes place on the basis of your Markovnikov's rule. The addition of HCl takes place on the basis of Markovnikov's rule, and the Markovnikov's rule said that the negative part of reagent adds to the carbon that having less number of hydrogen, okay. So in the reaction mechanism, it is nothing but the step-by-step explanation of your reaction mechanism. It is nothing but the step-by-step explanation of your reaction. This your propene react with H plus, okay. So the first step is your this double bond, your propene having double bond, carbon-carbon double bond. It's a high electron density center, so that pi bond will attack on this proton, okay. So it can attack from this carbon as well as this carbon, okay. So you will get the two different types of carbocation. Primary carbocation and secondary carbocation. So among these two, if this hydrogen add to this terminal CH2, okay, you will get this secondary carbocation, and if this hydrogen add to this middle carbon, okay, you will get the primary carbocation. So among these two, okay, you will get these two different types of carbocation, primary and secondary carbocation. Now among these two carbocation, this primary carbocation is less stable. Because this carbon is electron deficient species, and the group which increases the stability of that carbocation, okay, and the group that having which increases the stability. So here in this primary carbocation, okay, it having only one alkyl group, CH2 CH3, okay. So only one alkyl group is there to stabilize this carbocation, because this carbon is electron deficient, okay. In the last cell it having only how many electron? It having only 6 electron, okay. So this carbocation, it is a less stable, it's electron deficient species. So it is stabilized by the electron donating group. So this CH2 group is electron donating group, so it stabilizes this carbocation, and so it having only one electron donating group, it having only one alkyl group, while in secondary carbocation, it having two electron donating group, two electron donating group, that is CH3 so it is more stable, it is more stable because it having this two electron donating group. And one more reason is that, okay, one more reason is that this secondary carbocation, it having uh, it having 6 3 plus 3, it having 6 alpha hydrogen, it having 6 alpha hydrogen. It means that it having 6 hyperconjugative structure. We can write its 6 hyperconjugative structure. And uh, and the species with having more number of hyperconjugative structure, that will be more stable. Okay, so secondary carbocation having 6 hyperconjugative structures, so it will be more stable, while this primary carbocation having only 2 hyperconjugative structure, it's a less stable. Now in the second step, this Cl minus attack on this carbocation, Cl minus attack on this carbocation. Cl minus having negative charge, so this Cl minus, this is your electron rich species and this is your electron deficient species, so this Cl minus will attack and the Cl minus will form bond with this carbon. Cl minus will form bond with this carbon. Okay, so you know that this carbocation, secondary carbocation present in a major amount. Okay, so more number of carbocation present in a secondary carbocation, so this Cl minus will attack on this your secondary carbocation, and it is a more stable, so maximum number of carbocation present in a secondary form. So this Cl minus will attack on this Cl minus will attack on this carbocation, and you will get this 2-chloropropane as a major product, and very less amount of carbocation present in a primary carbocation. There is a very less amount of this primary carbocation are present, so this Cl minus attack on this, and you will get this 1-chloropropane as a minor product and 2-chloropropane as a major product. Okay, and this reaction involves Markovnikov's rule. This reaction involves Markovnikov's rule, the negative part of reagent. So in this HCl, the positive part is H and Cl minus is your negative part. Okay, so negative part of the reagent adds to the carbon that having less number of hydrogen, that is called as Markovnikov's rule. So here this your primary carbocation, and this carbocation having 2 hydrogen, and this carbocation the middle carbon having only 1 hydrogen. So negative part adds to the carbon that having less number of hydrogen. So this carbon having less number of hydrogen, so this reaction involves this reaction takes addition of HCl to propane takes place on the basis of Markovnikov's rule. So this is about the product analysis. Now let's take another example to understand this product analysis. So by analyzing the product, you can determine the mechanism of reaction. Now another example is product identification has been successfully used in knowing the correct mechanism for the Beckmann reagent. Product identification has been successfully used in knowing the correct mechanism for the Beckmann reagent. Okay, so you know the Beckmann reagent, Beckmann rearrangement reaction. So earlier it was believed that the oxime which yield this amide. Okay, so I will write that oxime. Okay, so earlier it was believed that the oxime which yield this amide passes the migratory group R dash near to the leaving group OH minus. However, later on it was found that one of the oxime, that is 2-bromo-5-nitro acetophenone, readily undergoes ring closure to form benzoisoxal, thus establishing its structure. So to understand, let me draw the structure of this 2-bromo-5-nitro acetophenone. So by analyzing the product, okay, by analyzing the product, we can determine the mechanism of this Beckmann rearrangement. So Let me draw the structure of 2-bromo-5-nitroacetophenone. 2-bromo-5-nitroacetophenone. Oxime of 2-bromo-5-nitroacetophenone. Br and OH. So this is the oxime of 5-nitro 2-bromo 2-bromo-5-nitro 1 2 3 4 5 2-bromo-5-nitro acetophenone, oxime of 2-bromo-5-nitro acetophenone, and its another isomer is anti one. This is your syn and anti. Syn, because this OH will get the first priority, and this is a carbon nitrogen bond. You know that the oxime are present in syn and anti. So here you have to use your CIP rule to find out whether it is syn or anti. So this OH will get the first priority, and this CH3 will get second side. This is 1 2 methyl group will get 2 second priority order. Okay, so these two same priority group present on opposite side to this carbon nitrogen double bond, opposite side to this carbon nitrogen double bond. So it's your anti. Now this will see this your oxime react with NH. O CH3O. So now listen, earlier it was believed that the oxime which yield amide, so you will get this amide, passes the migratory group R dash, consider this ring as a R dash group near to the leaving group OH, however later on it was found that one of the oxime, that is 2-bromo-5-nitroacetophenone, readily undergoes ring closure reaction to form benzoisoxazole second, thus establishing its structure. So the other isomer does not undergoes ring closure but readily yield Beckmann rearrangement product. The amide on identification leads to the conclusion that the Beckmann rearrangement reaction involves the transmigration of substituted phenyl group. Okay, so earlier it was believed that all the oxime undergoes your Beckmann rearrangement, but they have done this Beckmann rearrangement with these two isomer, syn and anti. So these are the two isomer. This is your syn and this is your anti. So this syn one undergoes ring closure reaction, not Beckmann rearrangement. Beckmann undergoes Beckmann, this carbon, okay, then there is a transmigration of this phenyl group. Then there is what? Transmigration of this phenyl group from this carbon to nitrogen, from this carbon to nitrogen. So let me show you. This phenyl group migrate from this whole phenyl group migrate from carbon to nitrogen, and this involves transmigration of your substituted phenyl group. Transmigration of substituted phenyl group. Transmigration of substituted phenyl group. Any doubt regarding this? Hello? Hello? काय समजतंय का रे? हॅलो? सगळ्यांना समजतंय? हेलो? समजतंय ना? ठीक है. ओके. राहुल कदम, did you understand? राहुल कदम? हाँ. मंगेश निरगुडे, सौरभ पाटील, विशाखा पाटील, विशाल जे, यस, मस्के श्रद्धा. हाँ, समझते करें. ओके. ठीक है. So by analyzing the product, this Beckmann rearrangement involves the transmigration of substituted phenyl group. Okay, so only the only the antioxime undergoes Beckmann rearrangement. Okay, so we can generally write this. Okay, we can write this is your general example of your oxime. General are R dash R dash. Example of oxime functional group. General example of oxime functional group: R N C CH3, CH2, CH3. ठीक है. So this is your starting material for Claisen rearrangement, that is allyl phenyl ether. Allyl phenyl ether. Allyl phenyl ether is converted by heating into ortho allyl phenol. Okay. So Claisen rearrangement, this allyl phenyl ether on heating. So here is your, not a CH3, it's a CH2. That's why there is a heating. Okay. So by heating, this is your ether functional group R O R, phenyl group R O R. This is your alpha carbon, CH2 alpha carbon, beta and gamma. Alpha, beta, gamma. This CH2 is your alpha carbon. Let's label for our simplicity. This is your alpha carbon, this is your beta carbon, and this CH2 is your gamma carbon. Okay. So when you heat this allyl phenyl ether, this is your allyl phenyl ether. By heating, okay, this compound undergoes Claisen rearrangement. This compound undergoes Claisen rearrangement. This compound undergoes Claisen. This compound undergoes Claisen rearrangement. Claisen rearrangement. Okay, after Claisen rearrangement, you will get ortho allyl phenol as a product. Ortho allyl phenol as a product. Okay. So you will get ortho allyl phenol as a product. So this is your OH, this is your ortho position, ortho okay. So this whole group CH2 alpha, beta, gamma migrate from this oxygen to this alpha carbon. Okay. CH two heat